so quick review from yesterday, okay? Newton's third law says that every action has an equal and opposite reaction. So if I push on something, it's going to push back. That's why I feel the pressure against my hand. That pressure is not from me pushing on the wall. That pressure that I feel in my hand is from the wall pushing back on me. Okay? That's the action-reaction pair, right? So in a situation like the one we're looking at right here, okay, they want us to find the force exerted by box B on box A, but they don't tell us very much, okay? So what we have to do is we have to recognize that first off, Newton's third law uses the math from Newton's second law, and that there's nothing really new in terms of what we do in terms of the forces, okay? What we have to do is break this system up into parts, okay? How do I know I have to break it up into parts to solve it? Why am I not solving it as a whole?
Force that's within the system.
Right, I'm trying to find a force that's within the system, not acting on the whole system. That means I have to break it up to find it, okay? So, what I want to do then is isolate the two masses. Alright, so I've got box A, which is 6.5 kilograms, okay? An applied force acting on box A causes both boxes to accelerate at 2.6 meters per second squared. Okay, that's useful. What can I get with that for each box? F net. Okay, that'll be helpful. All right, magnitude of the force of friction on box B is 28.3 newtons. Calculate the force exerted by box B on box A. Do they tell me anything about box A? Other than its mass and acceleration, right? Like I could calculate the net force on box A. Other than that, I know nothing about it, okay? I can say that, sure, here's the force from the hand. It's going to push box A that way. And what's the other force acting on box A?
Friction.
Okay, there's some friction there, but we don't know how much because they didn't tell us. And what's the other force acting on box A? Yeah, the force of B. That's the one they want me to find. Okay. I don't know any of those forces. And I don't really have any way to get any of them either. Not using box A anyway. Right? You guys follow my reasoning there? I can get the net force, I can go mass times acceleration, but there's no point. I don't know the other forces that add up to that number. So I kind of have to stop there with box A. I can't do this with box A. Right? Now, that's where people get frustrated because they're like, but that's the force I'm supposed to find. How am I supposed to find it if I don't have box A? We have to remember the most important part of Newton's third law. All forces act in pairs. So somewhere in this system is a force that is equal in magnitude to this one, but in the other direction. Okay. So that force then must be acting on which box? B. Okay. So I'm going to get rid of box A, and I'm going to start looking at box B. All right, so box B is heavier, 8.5 kilograms. What's that force? That's the force of A pushing on B. It's the only thing that's making B go that way, okay? Because the applied force of the hand is not acting directly on box B. It's acting on box B through or via box A. All right, is that force the action-reaction pair for the force I'm looking for?
Yes.
Okay, so now we're on to something. Now we know there's another force and we know where it is. Okay? What other forces are acting on box B? Friction. Okay, what else can I calculate about box B? F net. Yeah. Okay. Okay, so F net equals M times A, so that's going to be 8.5 times 2.6. All right, so the net force acting on box B is 22.1 newtons. All right, now this becomes a Newton's second law problem. I've got net force by going M times A. What's the other way to get net force?
Sum of all.
Sum of all forces. So, two forces acting on box B, and I know the net and I know the friction. So I know 2 out of the 3 forces here. So I'm gonna isolate the one I don't know. Okay, force of A on B by subtracting the force of friction. Now, what do I need to keep in mind here that sometimes people will forget about friction? It's negative. Okay, that's the thing people will forget. Okay, so I'm going to take my 22.1 newtons forwards and subtract 28.3 newtons backwards, and that will give me my force of A on B. Okay, so the force of A on B is 50.4 newtons forward. So what's the force of B on A? 50.4 newtons backwards. Actually, we only have 2 significant digits, so it would just be 50 newtons backwards. Okay? Is there a heck of a lot of analysis that has to go on to solve that problem? Yeah, there is. Okay? There's no difficult math. Okay? It's all adding and subtracting and multiplying. Like, there's nothing really strenuous about the math, but there is a lot of strenuous analysis that has to go on to figure out all those little tiny relationships. All right, I'm going to give you one that's like this, but it's going to be like the one you're going to get on your unit exam. Okay? Spoiling a question on your unit exam. Okay, this person has longer arms than they have legs, don't laugh. Okay, so long-armed person is pushing on box A, okay, directly. That's causing both boxes to accelerate at 1.85 meters per second squared forwards. The floor that they are on is level and frictionless. We are looking for the force that B exerts on A. So it's actually a little easier than the one we just did. It's 2 boxes, but there's no friction on this one, so it actually makes it a little easier. Okay, so I'm trying to find the force that B exerts on A. Which box should I use to get it?
B.
Yeah, I have to use box B. I don't know the force being applied directly to A, so as a result, I can't do any sum of all forces calculations with A, because I don't know either of the forces. I know what they add up to, but I don't know either of the forces, so I can't use A. But I can use B, okay? Because on box B, all right, that is 8.0 kilograms, okay? I've got the force of A on B, which is the action-reaction pair for the force they want, B on A. Are there any other forces acting on B? Nope, there's no friction, okay? There's nothing else there, there's no box in front of it. Okay, so then the force of A on B is actually the
Net force.
net force. Does that make this question like super easy? And I have way less to do than the previous one that involved friction. All I have to do is go 8 times the acceleration, which we said was 1.85. Okay, so that's F net equals m times A, and that's also going to equal the force of A on B. All right, so 8 times 1.85. Okay, 14.8 newtons. Right, so there's my force, 2 significant digits. I'm looking at 15 newtons backwards for the force of B on A. Right? Yeah, you still have to do a bit of like analysis in there. You still have to break it up into the 2 boxes, but that one ends up being a bit easier. Okay? But it tells me whether you understand that whole action-reaction pair idea, that you can find the force you're looking for by finding the force you're not looking for. Okay, that's kind of the confusing part of Newton's third law. You find the force you're looking for by not finding the force you're looking for.
So is A on B the same as B on A?
Right. Okay, because they're, like, when A pushes on B, B pushes back with the same amount, right? So that's why we can say, if I find one side of the pair, I know both. Okay, all right. This is probably the best question in the whole book. Okay? So, I want you guys to give it a try. I might have to make it smaller so you can see the whole thing here. All right, so in this question here, we've got horses that are pulling 2 logs, and the logs are attached to the horses by a chain, and they're attached to each other by a chain. So it's kind of like that 2 boxes question we did right at the very beginning. They weren't touching each other, but they were connected by a rope. Okay, so it's a similar question to that. Okay, we know the masses of the 2 logs, right? We know the force the horses can exert, so we can pretty straightforward calculate the acceleration of the logs and calculate the force exerted by log B on log A. All right, I'll give you guys a bit of time to draw that one out and get it tried, okay, and then we'll walk through it together. Answers are right here if you want to check them. Okay, let's have a look at this one. So our diagram kind of ends up looking like this. This is log B, which is 250 kilograms. And it's attached to log A, which is 150 kilograms. Okay, and they're attached to the horses. Okay. So the horses can pull with a combined force of 2,600 newtons. The ground exerts a force of friction of 2,400 newtons on the logs, plural. All right, so they're in part A treating this as a system. All right, so that means then that I'm going to have 400 kilograms, okay, 2,400 this way, 2,600 this way. Okay, that's going to give me a net force on the whole system of 200 newtons forwards. All right, then I can calculate the acceleration of the system simply by going 200 newtons divided by 400 kilograms, which is going to give me 0.5 meters per second squared forward. All right, so that's part A. I've got the acceleration of the system, of log B, of log A. All right, now I can use that to figure out, okay, the other stuff here for question B. Just pick it up. Okay, so for part B, the force of friction on log A is 900 newtons. Calculate the force exerted by log B on log A. Which log should I use? I can actually use either one. Okay, it's an action-reaction pair, so I can use either one of these logs to figure this one out. I would actually use log A. I have one less step if I use log A because they told me what the friction is on log A. I'd have to figure out what the friction is on log B. It's not hard, I just have to subtract, but it's an extra step. All right, so I'm going to isolate log A, say 150 kilograms. Okay, force forward on log A is 2,600 newtons because that's the one the horses are directly attached to. There are two forces pulling back on log A. The force of friction and the force of B on A, which is the force they want me to find. Okay. I can find the net force on log A because I know the acceleration of log A. So I'm going to calculate that next. Mass times acceleration. Okay, so 150 times 0.5 is going to give me positive 75 newtons. Right? So I got 75 newtons forward as the net force on log A. Since I know the applied force forwards and I know the force of friction to be 900 newtons, I can calculate the force of B on A because it's the only one I don't have. So I go to sum of all forces, and I say F net equals the applied force plus the force of friction plus the force of B on A, and I simply subtract these two over to the other side. So I'll have F net minus the force of friction minus the applied force equals the force of B on A. Okay, so that'll be positive 75 minus negative 900 minus 2,600, which is positive because it's forwards. Okay, that's going to leave me with a negative number, which makes sense. The force that B exerts on A would be directed backwards. All right, so 75 minus negative 900 minus 2,600 gives me 1.63 times 10 to the 3 newtons backwards. Okay, actually they only ask, oh no, they do ask for the force exerted, so I would have to say backwards. Okay, on that one. If they ask for the tension in the chain, would I have to list backwards? Okay, did you have to pick that one apart again? You did. And you could have solved it with log B, a lot of people do. Okay, perfectly legitimate to do that. You just have to take that 2,400 newtons and subtract the 900 newtons of friction from the first one, so you got 1,500 newtons worth of friction on log B, and then you do the same thing. Okay, everybody all right with that one? Okay, going to give you about a 5-minute break here, and then we're going to look at the math of that everybody jump thing that we looked at yesterday, or that we talked about yesterday after we watched the stupid Nike ad about turning the earth with your feet. All right, give you 5 minutes here, guys. Okay, so yesterday we were talking about this situation after we watched the Nike ad. And if you got everybody in one place and they all jumped at the same time, you'd knock Earth out of orbit, and the world would end. It'd be all very bad. Okay, so at the start of this scenario, the entire Earth's population has been magically transported into one place, because of course that's the only way we could do it is by magic. Okay? So the crowd takes up an area the size of Rhode Island, not just the size of Rhode Island, we put them in Rhode Island, the smallest state in the Union, but when you pack a bunch of people shoulder to shoulder, that's how much room they would take up. Okay? At the stroke of noon, everyone jumps. Because, you know, in an area that geographically large, that would be possible that everyone would jump at exactly the same time. Okay? So it doesn't really affect the Earth. The Earth outweighs us by a factor of over 10 trillion. Okay? We showed that yesterday. On average, we humans can vertically jump maybe a half a meter on a good day. Even if the Earth were rigid and responded instantly, it would be pushed down by less than an atom's width. Next, everyone falls back to the ground. Okay? Technically, this delivers a lot of energy to the Earth, but it's spread out over a large enough area that it doesn't do much more than leave footprints in a lot of gardens. A slight pulse of pressure spreads through the North American continental crust and dissipates with little effect. There'd be kind of a rumbling sound that you would hear, okay? And that would be about it, okay? Eventually, the air grows quiet. Seconds pass. Everyone looks around. Why did we do that? What are we doing here? Okay? There are a lot of uncomfortable glasses. Someone coughs, which now would probably cause panic, because you wouldn't put 7 billion people all in the same place ever, but post-COVID especially. Okay? That doesn't seem like a good idea. Okay? A cell phone comes out of a pocket. Within seconds, the rest of the world's 5 billion phones follow, okay? All of them, even those compatible with the region's towers, are displaying some version of no signal because the cell networks have collapsed under the unprecedented load of 5 billion phones, okay? Outside Rhode Island, abandoned machinery begins grinding to a halt, okay? The airport in Warwick, Rhode Island handles a few thousand passengers a day. Assuming they got things organized, including getting fuel, they could run at 500% capacity for years without making a dent in the crowd. Okay, so we're starting to come up on some problems here. Okay, so we're trying to get everybody out of Rhode Island somehow. Okay, the addition of nearby airports doesn't change the equation much, nor does the region's light rail system. Crowds climb on board container ships in the Deepwater Port of Providence, but stocking sufficient food for water for a long sea voyage is a challenge. Okay, Rhode Island's 500,000 cars are commandeered, but I-95, I-195, and I-295 become the sites of the largest traffic jam in the history of the planet. Most of the cars are engulfed by the crowds. It sounds like something out of The Walking Dead. Okay, but a lucky few get out and begin wandering the abandoned road network. Some make it past New York or Boston before they run out of fuel. Since the electricity is not on anymore, you can't go to a gas station and get gas, even if you were just going to steal it. The pumps aren't working. So, steal another car. Because that's a thing. All the cops are in Rhode Island. Okay, who's going to stop you? And society begins breaking down. Okay, so we get a problem here. Okay, grocery stores are emptied, fresh water is hard to come by, nobody's talking about the sanitation problem. There's 7 billion people who all have to go to the bathroom. Yeah. So, yeah, we're only talking about food and water here. We're not talking about the really gross part of having 7 billion people in one place. Okay, within weeks, Rhode Island is a graveyard of billions. Sad. Okay. Survivors spread out across the face of the world and struggle to build a new civilization atop the pristine ruins of the old. The species staggers on, but our population has been greatly reduced. Earth's orbit is completely unaffected. It spins along happily as it did before our species-wide jump. So, pointless. Can't do it, okay? People running in the same direction doesn't reverse the spin of the Earth, okay, or anything like that. But here's the math of it, okay? Well, or kind of some other problems with it. How would you synchronize that jump? And can you just use like a starting pistol, fire it, and everybody would jump? Why not?
Sound.
Yeah, it's sound. First off, Rhode Island is really big. If I fire a gun even in the middle of Rhode Island, you're only going to hear that for about a kilometer-wide area around the point of firing. Okay? The other part of that kilometer-wide area of firing is that it takes sound 3 seconds to travel 1 kilometer. So when I fire the gun, the people right next to me jump, and the people that are a kilometer away are like 1,000, 2, 1, bang! Oh, okay, now I'll jump. I'm not getting everybody to jump at the same time using sound. Now, could I use a big light? It'd be better, at least it would be instant, but the problem is, if you're over the horizon, you don't see the light, and we would have that problem in Rhode Island.
Like a countdown.
Okay, we could have a countdown, but how would everyone get the signal?
I feel like if you did it like the same countdown, but like you would spread it, like distances where everyone can hear it at the same time.
To have some like towers?
I feel like not towers, but like maybe like speakers.
Okay, towers or speakers, okay? I mean, the signal would be more instantaneous that way, but the speakers would have to be less than 100 meters apart to negate that sound traveling at a finite speed thing, yeah.
You also have to account for everyone's reaction times and how, like, a baby's not gonna jump as fast, or a grandma who's like 104 isn't gonna jump
Yeah.
as fast as.
And if there's people with disabilities, they can't jump, not everybody's gonna jump. Yeah, but we can only get the people who can jump to jump, okay? If you're like me and you got a credit card vertical, okay? You guys know what that means, right? It means I couldn't jump over a credit card lying down on the floor. Okay? Okay. So, we have all these differences. We're making assumptions, right? They said people can jump about a half a meter on a good day. I mean, I used to be able to jump, but that was when I was young, okay? I'm not young anymore. So half a meter that's a challenge for me now, okay? So all of those are kind of problems, okay? The other big problem, and it's never addressed, you're not gonna have 7 billion people paying attention. Okay? I mean, this is my thing, okay? My whole job revolves around having people's attention. I can't have all of your attention at the same time. How am I gonna have 7 billion people's attention? Driving down the road, people aren't paying attention to driving, okay? They're gonna be, oh, I should jump now? What if they're on their phone? What if they're texting their friend? They're gonna miss the signal, okay? And they're not gonna jump. It's terrible. The idea of synchronizing that jump is crazy, okay? All right, calculate the total mass of the Earth's population, assuming the average mass is 65 kilograms. Okay, so 7 billion people. Okay, so we calculated that number yesterday. Okay? That's the mass of the Earth's population. All right.
What if you put, this is completely up there, but what if you put everyone in those like harnesses that they do and all pulled them up at the same time so that everyone did, actually that wouldn't work because then you're not pushing them.
What kind of harness?
And then drop them,
I don't know.
and then drop them all at the same time.
Yeah.
Well, I mean, it doesn't matter how they make contact with the Earth, right? I mean, drop them, people are gonna get hurt, okay? And are all 7 billion harnesses going to work? I mean, there's gotta be a failure rate of some percentage there, right? Yeah. So calculate the total gravitational potential energy of the crowd when they are at the maximum height of their jump. So think back to Science 10. Gravitational potential energy is mass times gravity times the height. Okay, and we said earlier that they are all going to reach a height of half a meter. So we're going to say that 4.55 times 10 to the 11, that's our mass, times 9.81 times a half a meter. Okay, so there's the energy that the crowd will have when it comes back down to the ground. Okay, assuming law of conservation of energy applies here. Okay, so 2.23 times 10 to the 12 joules. That's a lot. Okay. All right, so question number 4, determine the kinetic energy of the crowd as they strike the Earth after they fall. It's that number. Law of conservation of energy says if I have that much potential, when I fall back to the ground, it'll all convert to kinetic. Does that ring a bell? We're going to talk about that after Easter, but okay. So that's number 5. So determine the maximum kinetic energy of the Earth as the result of the crowd hitting it. We have that number already. It's the number we just calculated. Calculate the maximum speed of the Earth. Okay, so for kinetic energy, the formula is 1/2 mv squared. Okay, everybody with me there? So I'm trying to calculate the speed the Earth will gain as a result of the energy we just calculated. So the energy we just calculated, we're putting in here. Okay, what am I going to put in for m? Mass of the Earth this time. Okay, because I'm trying to figure out what the speed change of the Earth will be as a result of this much energy. So I'm going to divide both sides by half of the Earth's mass, and then I'm going to square root that to get v. Okay, so I'm going to take that number, right? We're going to divide that by 0.5 times 5.98 E24. Okay, that's the mass of the Earth. And then we're going to square root that. So the speed of the Earth will change by 8.6 times 10 to the minus 7 meters per second. So that's 8.6 nanometers per second. No. Yes. Yeah, something like that. It's ridiculously small, okay? We're not going to detect that, and it's sure not going to knock the Earth out of orbit. The Earth's speed changes by, well, factors of billions more than that, because the moon pulls on it, okay? So, yeah, this is not going to do anything.
I don't know, this isn't realistic either, but say you got 8 billion people, flew everyone to the moon, and we did that on the moon.
Mhm.
Well, I guess no, that wouldn't work because gravity, the way, like, yeah, never mind. But if
You're-
if
yeah,
you're
you're-
on a planet with the same, like, pull of gravity as Earth that was, like, smaller than the moon, and we did that, then would anything change? Probably.
Yeah, because the mass would be smaller. The problem is that it'd be very difficult to find a place where the mass could be that much smaller, but the acceleration due to gravity be the same.
Right.
Because the acceleration due to gravity is factored in, is part of that is the mass of the Earth. Yeah. Okay, so we see now that mathematically it's ridiculous. All right, I'm going to give you guys a little bit extra time to work on your Newton assignment because that's all I want to cover today. So if you want to work a little more on your Newton assignment and get it done, have at it.
How long does it take to walk around the moon?
I don't know. I don't think anyone